Hello and welcome to my channel. My name is Adriaan and today we are going to continue using Ricardo WAVE, and in front of you will see a 4-cylinder spark ignition engine. This is the engine that you can get from the Ricardo files, so you can just go to Ricardo's files under program files, and under the tutorials tab or under the tutorials folder you will get this 4-cylinder spark ignition engine. Now in today's video I'm going to show you how to modify this engine to run on an Atkinson cycle. Let's get started. So before I get into changing the model, we first need to understand what is the Atkinson cycle and what benefit does it add to an engine. Now if we go into internal combustion engine fundamentals by Haywood and we read what their definition is, it states that the gas pressure within the cylinder of a conventional 4-stroke engine like the one you see here and exhaust valve opening is greater than the exhaust pressure. So the available energy of the cylinder gases at this point in the cylinder is then dissipated in the exhaust blowdown process. It's lost. We can't use it. And additional expansion within the engine cylinder would increase the indicated work per cycle. If we managed to expand it further, we could have used this energy. So looking at the figure, additional expansion within the engine cylinder would increase the indicated work per cycle. The expansion continues beyond 0.4-, which is our conventional ideal cycle exhaust valve opening point. Now, complete expansion within the cylinder to exhaust pressure P exhaust, which is at 0.5 *, is called the Atkinson cycle. So many crank and valve mechanisms have been proposed to try and achieve this additional expansion. So it can be achieved in a conventional 4-stroke cycle engine by suitable choice of exhaust valve opening and intake valve closing positions relative to bottom center. And this next sentence we are going to use to test to see if our engine is sort of exhibiting Atkinson cycle-like behavior. Haywood states that if the crank angle between the exhaust valve opening and bottom center on the expansion stroke is less than the crank angle between bottom center and intake valve closing on the compression stroke, then the actual volumetric expansion ratio is greater than the actual volumetric compression ratio. So this effect of overexpansion will increase efficiency and ultimately improve fuel consumption. So let's see if we can achieve this in our WAVE model. First off, we're going to have a look at this valve opening and closing characteristics of our engine. So we're going to select our cylinder and we're going to add an output file or an output graph for the valve lifts, which is graph 142. So now when we run the model, it will generate a valve lift profile graph that we can have a look at to see where is this closing of the intake valve to bottom dead center and where is the opening of the exhaust valve relative to bottom dead center. So we can run this model. So once the solver is finished, we can go to the post processor, WavePost, and have a look at our valve lift profile. So once WavePost has been opened up, we can go to the left, we can select our valve lift graph, and here you can see our valve lift profiles for inlet and exhaust valves. Now specifically we're interested to see the distance between inlet valve closing and bottom dead center and exhaust valve opening and bottom dead center. So for intake valve closing, you can see that it is about 70 degrees after bottom dead center that it closes, and for the exhaust valve it is also 70 degrees before bottom dead center that it opens up. So it's equal. So currently this engine is not in an Atkinson cycle like environment, so we need to go and increase the distance between inlet valve closing and bottom dead center to try and simulate or to try and get the engine to operate in Atkinson-like environment. Now before it closes, you will see here at the right top there's WAVE files listed, Atkinson-based wavesolver.wvd and .sum files. So those two files you now need to go and give them another name and save them so that we can use them in our next post-processor session to compare it with the changes that we made. So I am just going to quickly go and save them as different file names. Right, so once you've saved your output files with an appropriate name, we're going to go back to our WAVE model and we are going to click on our inlet valve. You can click on any one, it doesn't matter. And then we're going to go over to our properties window and we are going to edit our lift profile by clicking on the little pencil button. Now looking at this, we can easily increase the duration of the inlet valve open time by going to the multipliers and changing our duration multiplier, which is currently set to 1, and we're going to increase it by 10%. So we're going to multiply it by 1.1, and this essentially means that the duration is increased by 10%. You can see this visually happening if this is our valve lift profile for our intake valve, and you can see as I change it, the multiplier from 1, you can see that duration decreases, and as I increase it to 1.1, it will increase again. So that's a quite nice quick way to manipulate the open duration of the inlet valve. You can just use the multiplier for the duration. So let's see if we've managed to change this engine model to operate in an Atkinson cycle environment. So we're going to run the model again. Once the solver is done, we can again head on over to our post processor, WavePost. And before we look at any graphs, we need to add our baseline results that we saved after we ran the first model. Now to do that, we can go to our little window here, and we just click on the button add, and then we can add our base folder with the extension WVD, and it will automatically add the sum one as well. And then Wave asks you if it can include all this newly added data to the existing graph, so we're just going to say yes because we want to compare data. And now if we select our valve lift profile graph, we can see from our valve lifts that our inlet valve closing time has shifted to approximately 100 degrees after bottom dead center. So now the inlet valve is open for 20 degrees longer, and as such our expansion ratio is bigger than our compression ratio. And according to the definition that we saw at the start of the video, this will put us in a sort of Atkinson-like environment. Now let's see if this is the case. Now to see that, I'm going to replicate some graphs that I saw in a journal article, and we are going to compare brake specific fuel consumption as a function of brake mean effective pressure. Now that graph is not automatically generated inside WavePost, so we need to create it. And to create any new graph, we're going to go here at the top and we're going to say add, and we want to sweep plot, and it's a 2D plot. A window then opens with an empty graph. So now we need to go and we need to add some data. So again, we are going to click on our add button, and because we've generated all the data inside Wave, we're going to select Wave data, and this again opens up a window, and you can see here is my two sources listed: my base source, which essentially is all the data that I've saved, and then the other source, which is the most recent run that I had. Something that will make your life much easier is to ensure that this option is checked, and then it'll be much easier to select the x-axis and y-axis values. So for our y-axis, our dependent variable, we want our brake specific fuel consumption. So if we scroll down, we have brake specific fuel consumption SI, so it's in SI units. You can also go with the British units if you want to. I'm going to go with SI units. And then for our independent variable, it is our brake mean effective pressure, which is over there. And if we select that, we can see that with increasing brake mean effective pressure, we have a decrease in brake specific fuel consumption. Now this is for our latest solution. So now we're going to add our baseline, where we haven't made any changes to the duration of our inlet valve opening time. So again, we're going to add Wave data, and this time we're going to select our base data points, which is the ones that we saved. Again, we're going to make sure that it's alphabetically listed, and we are going to select our brake specific fuel consumption as a function of BMEP. And here you can clearly see that for the base configuration, which is not Atkinson enabled, so that we didn't change anything to the valves, we have much higher brake specific fuel consumption for areas of brake mean effective pressure of 9.5 to 10.5. And then when we increase the duration of our inlet valve open time, effectively making sure the expansion ratio is increased, we have reduced our fuel consumption. And by doing some rough calculations for those data points on the graph, if we take the example of 10 MEP, we get a fuel saving of approximately 5%. And that is achieved by only increasing our inlet valve duration by 10%. So that is quite a nice visualization to see that. Another benefit of the Atkinson cycle is that it decreases pumping losses. So when you make the inlet valve close time later, your pumping losses is decreased, and we can see this visually as well by looking at a graph and comparing our two data sets with each other. So let's do that now. And there you can see by increasing the open duration time of our inlet valve, our pumping losses has decreased considerably. Again, if we take the example of 10 BMEP, you can see that the pumping losses has decreased by almost 75% as a result of that. Now, obviously, there are downfalls to using the Atkinson cycle, and you can see by this graph, we have a decreased torque and power output because our red graph has shifted to the left versus our blue graph as much can reach 12 BMEP, where our Atkinson enabled engine only comes up to about 10.2 BMEP. The power production and the torque output of this engine is reduced, but its efficiency is increased. There's a video by Engineering Explained which nicely shows this visually as well, and it also discusses the benefits and downfalls to using the Atkinson cycle. And you will see predominantly in hybrid vehicles, Atkinson engines are used because the electric motor is able to compensate for that reduced torque and power output while still having that nice efficient fuel consumption for the internal combustion engine. And that's it. This is a quick example just to show you the benefits of the Atkinson cycle and how you can actually model that in Wave and see it visually on graphs. I hope you've enjoyed this video. If you've got any questions, please do not hesitate to put them in the comments down below. You can also connect with me on Twitter or LinkedIn and send me any questions that you might have on that platforms as well. Thank you very much for watching, and I will see you in the next video. Bye.